Hey folks, welcome to Total Physics. This is Keen. Today we're going to talk about measurements. Let's start with a little introduction to get a sense of why we care about measurements. In physics, we attempt to formulate a relatively small number of laws to describe a wide range of phenomena, from how rainbows are formed to how the universe was born. In fact, physicists have wonderful stories to tell about all these things and many more. But what makes physics a science instead of a wonderful bedtime story is experiments. Every theory in physics, no matter how wonderful it is, has to be tested in experiments. In experiments, we measure things. That's why measurements are very important. But how can measurements be so powerful? How can they promote a story to the status of a scientific theory? To answer that question, I would like you to consider another question. Here's a picture with two yellow circles. Can you tell me which yellow circle appears larger? Most of us would say the circle on the left looks larger, but in fact, both circles are exactly the same. This is an example of optical illusions. Optical illusions like this are very common and they fool us all the time. But they can't fool our measurements. If you were to place a ruler on top of each yellow circle and measure its size, you get the same exact measurements for both circles. Thus, measurements are very powerful. They can bypass our limitation and allow us to probe reality more objectively. Now that we've established that measurements are cool, let's talk about the things we can measure, or physical quantities. Physical quantities are physical properties of a phenomenon or an object that can be measured. Examples are the length of your cat's tail, the mass of your dog, the time it takes for you to finish a 5K marathon, the speed of your car on the highway, and the force of a crocodile's bite. We can measure all these things, so they are physical quantities. It's also helpful to think of physical quantities as the vocabulary of physics. Without physical quantities, physicists will not be able to express their ideas precisely. As we proceed through this course, we will learn more physical quantities besides the ones I just mentioned. Lastly, a physical quantity is often expressed by a number with a unit. For example, Robert Wadlow's height was 2.72 meters, which is almost 9 feet, making him the tallest man in recorded history. Robert Wadlow's height is a measurable property of Robert Wadlow, so it is a physical quantity. Here are two ways of expressing that physical quantity, but each consists of a number and a unit. 2.72 is a number, and meter is a unit. Similarly, 9 is a number, and feet is a unit. Now, what is a unit? How do we know how long a meter is? Well, most of us would probably look it up on Google if we don't know. But how does Google know how long a meter is? The answer is standards. Standards define the meanings of units. Standards can be physical objects or just abstract ideas. For example, historically, the human foot was the standard used to define the unit foot. 1 foot was just the length of your foot. Ideally, all standards used to define units should be invariable, meaning they don't change over time and easily accessible. It should be invariable so that you won't be 5'9" one day and 6'7" the next day. That would be too confusing. It should be easily accessible because imagine how slowly science would be making progress if you have to ask for your mom's permission every time you need to use a ruler. Anyway, the unit foot defined by a human foot is clearly not ideal. Yes, most people have feet so it is easily accessible, but the size of a human foot is not invariable. First, it varies from one person to another. Secondly, it even varies over time for the same individual. I bet your foot size is much smaller when you were a baby. Nowadays, the unit foot was redefined to be exactly 12 inches, which is about the average length of a human foot. This is an example of how a standard changed from a physical object to an abstract idea. Incidentally, an American college football is also about a foot long. For you soccer fans out there, here's another reason to call an American football a football. Now, do we need a standard for every physical quantity? Luckily, no. It is easier to establish standards for certain quantities such as length and time than other quantities such as force. Because of that, quantities such as length and time are known as base quantities. There are only 7 base quantities. All other physical quantities such as speed and force can be derived from these base quantities, so we call them derived quantities. Here's the complete list of base quantities. I'll list the quantities in the left column and their units in the middle and right columns. SI units are the International System of Units. We'll talk more about them in a minute. The first base quantity is length. The SI units is meter and its symbol is little m. We've seen this earlier when we quoted Robert Wadlow's height as 2.72 meters. The second base quantity is time. Its SI units is second, and its shorthand is a little s. We all know what a second is. The third base quantity is mass. Its SI units is kilogram or simply kg, little k and little g. This unit is related to the weight of an object. The next one is amount of substance, with the SI units mole or simply mole, spelled M-O-L. This is how desperate physicists are when it comes to creating shorthands. Even just getting rid of one letter makes us happier. This physical quantity usually shows up in chemistry, but we may use it a little bit in this course too. Temperature is another base quantity. Its SI units is Kelvin, and the symbol of the unit is capital K. Kelvin is not a common unit in everyday life. We usually only use degrees Celsius or degree Fahrenheit. However, Kelvin is commonly used in physics. Electric currents is also a base quantity. Its SI units is ampere, represented by a capital A. You may have seen these units on your phone charger before. And the last base quantity is luminous intensity. Its SI units is candela or simply CD. Roughly speaking, luminous intensity measures how strong a light source is. In this course, the base quantities that we'll mainly use are length, time, mass, and temperature. Alright, let's talk about systems of units. The average distance between the moon and the earth is 238,900 miles. If you're not familiar with miles, that's just equal to 384,400,000 meters. As you can see, there is more than one way of stating the same measurements because there is more than one system of units. In this section, we'll look at the three most common systems of units, namely SI, British, and Gaussian. SI or International System of Units are generally used in science and by most countries. We will mainly use SI units in this course. You may be wondering why it is called SI. Shouldn't it be called IS for International System? Well, SI stands for Système International, which means International System in French. Yep, gotta know French to do physics too.
1, 2, 3.
SI units are also complemented by SI prefixes, making it easier to express very large and very small quantities. For example, the size of your computer storage might be 1 million bytes. It may take you a second to understand how big that is, but if I put it this way, 1 terabyte, then you know exactly what that means. The big T, which stands for tera, is a prefix. Here are some of the common prefixes. This table is more than enough for us and even for most, if not all, physics PhDs. Frankly, I've never even used exa, hecto, deca, deci, or atto before. Don't even know if I pronounced the last one right. Notice that the left half of the table consists of prefixes that represent positive powers of tens, while the right half consists of those with negative powers of tens. If we look at tera again, we see that it represents 10 to the 12th power, or 1 million as we saw in the previous slide. The way we use a prefix is by putting the prefix in front of a unit. So we would say terabytes instead of byte tera, which sounds terrible. The next system of units is the British Imperial System. The British Imperial System is only fully implemented in 3 countries, Burma or Myanmar, depending on your political inclination, Liberia, and the United States. The rest of the world mostly uses SI units. There are about 200 countries in the world, but why aren't there more countries using the British Imperial System officially? One reason might be that the British Imperial System does not have prefixes like the International System does. You never hear anyone say, "I just ran 5 kilojards today." Because of this, the British units of length is quite amazing. In this chart, you see how the various British units of length are related to one another. 20 twips is a point, 63 points is a finger, and 4 poppy seeds is a barley corn, and so on. The SI units shown on the right here are much cleaner. 1000 micrometers is a millimeter, 10 millimeters is a centimeter, etc. Thankfully, we're only mostly using SI units in this course. The last major system of units is the Gaussian system. The Gaussian system of units is also known as the CGS system. CGS stands for centimeter, gram, second. Most people are not familiar with this system of units, but the Gaussian system is commonly used in the literature of physics. This is because it has the advantage of simplifying certain equations in physics. For example, Coulomb's law in SI units is this, but in Gaussian units, it simplifies to this. We effectively got rid of the complicated looking term up front just by switching to Gaussian system. We'll talk more about Coulomb's law when we study electromagnetism in the next course, so stay tuned. If you think having so many systems of units is confusing, you're not alone. This is a problem even for the experts. In February 2001, Clarence, a 250 kilogram tortoise, wrecked its new home at Moore Park College, California by pushing over a fence pole designed to confine a 250 pounds tortoise. That happened because the zoo told the college that Clarence weighed about 250, but no one bothered to ask 250 what. Another more disastrous case happened in September 1999. A $125 million spacecraft called Mars Climate Orbiter crashed into Mars because a computer program that should have provided outputs in SI units provided outputs in British units instead. We certainly have a knack of creating trouble for ourselves.